Yes. Thank you all for coming. Thanks to the National University, the Conservatory, the Institute of Mathematical Sciences for hosting this. And thanks especially to Elaine Cho for inviting me to speak and also for assisting me on the piano with some of these canons. So I'm going to be talking about infinite canons, but before we get to that, I'm going to talk about a couple of canons that we haven't discussed yet. Moreno touched upon it. Canons by augmentation or diminution, or we might think of as a tempo canon, a situation where in the canon they sing the lines or play the lines but at different tempos. This is, to the best of my knowledge, the first notated example of this from the late 14th century by Johannes Ciconia. This is the 3. Now 3 against 1. Against 3 against 1. It does my heart good to know over 600 years ago people were doing this and really interested in it. Another thing to talk about are what are called puzzle canons, or the idea of a canon as a puzzle that has a solution, or possibly more than one solution. This is one of these puzzle canons from the musical offering by Bach, and he gives and etc., and writes this Latin phrase, which basically means look for it yourself. You'll find it. He doesn't tell you how the canon is going to work. He gives you one big clue. The second clef is a regular bass clef, except it's upside down, which means that you're going to invert this. And so where it goes up, it should go down. If you play around with it enough, you'll find a solution. I should have practiced with the alto clef before, but here we go. Okay, so that's a solution, yes. So you should be done, except there's actually 2 solutions to this. The inverted voice can lead. Canons can have multiple solutions. This leads to a natural question. How many solutions can one canon line have? Is 2 the max? Is 3, 5? Is there any limit to it? The answer is no. You can create canons that have an infinite number of solutions. Now, we should be careful with this idea of a solution, because as Noam was saying, you could just throw any line by itself and say it's solved. But what we want is not anything goes. We want to have some constraints. In the canons that I'm talking about, the constraint is that they are harmonically consistent. That is, if you hear dissonant chords, you hear dissonant chords consistently. If you hear consonant harmonies, then you're going to hear that consistently. And very specific ones. If you hear a tenth, you will hear tenths throughout. But these canons have to have a property of maximally self-similar. Let's talk about the self-similar part. This is from Tom Johnson. And here's the line up top. And it repeats. If we take that line and we perform it 3 times as slow, and we perform it with the original, every time the slower voice moves to the next note, it forms, in this case, an octave. So the original canon line has within itself its own version 3 times as slow. And we would say it's self-similar at 3-to-1. We can do one tiny trick that makes a big difference, and I'm going to play it again, but I'm going to take the right hand, or the upper part, and I'm going to move it up by 1/3. So we don't hear a series of octaves. Instead, we hear a series of parallel tenths, which are a nice consonant interval, probably the single most common interval that you hear in traditional classical repertoire. Okay, to my ear, this makes a big difference, because I'm not drawn to the self-similarity. What I hear is this canon by augmentation, this tempo canon at a 3-to-1 ratio. So this is the connection with self-similar canons and tempo canons. Now to get to the maximally part of it, we can start with a very, very familiar musical object. If I play this low A, the string will vibrate as a whole, but it will also vibrate in 2 parts, 3 parts, 4 parts, etc. And each of those modes of vibration will give you a different frequency, and this gives us the harmonic series. I played the first 16 of those. If we take every other one, we get this. Which is the same line up an octave. If we take every 3rd, we get the same line up an octave and a 5th. So really, the idea of maximally self-similar is built into virtually every note that we hear. And this is the basic mode of tone production on brass instruments. This is how you get higher registers on wind instruments. String instruments do it. It's very common. We can do the same trick as we did with the Johnson, which is we can now transpose them and form a canon out of it. Here we have a canon 1 to 2 to 3, where they're going to form stacked fifths. Every time one of them changes, they're sounding either a 5th or 2 5ths together, which makes a 9th. No. Okay. Now let's try to understand what's going on with this, with the harmonic series. This notion of maximal similarity can be modeled by a logarithmic spiral. This is a spiral that moves at a constant rate of expansion from the center. If you look at the first point there labeled 1, and as the spiral goes around, it crosses the x-axis, and it's twice as far from the origin, 2. By the next time it goes around, it's at 4 from the octave, then 8, and then 16. So it's constantly doubling throughout. We can label points when they get to, say, integer distances away from the origin. So we have 3 and 5 and 7, etc. Now we've taken the space and we've divided it up into these wedges. These wedges correspond to an ascending, if we go in a counterclockwise manner, to an ascending chromatic scale. If we associate each one of these points with the slice that it's in, we get the overtone series. We could collapse it into an octave, but we won't. An A, C sharp, E, G, A, etc. So the harmonic series is great for demonstrating this maximal self-similarity, but it's not all that useful melodically. So what we want to do is abstract away. And basically the thing to take away from the slide is we've removed the names of the slices that we have. We can put anything in there, and we will have a self-similar melody that results from it. So essentially we can have the harmonic series, but not, with its own interval cycle. Let's fill it up with something different, is this. So what we have here is a cycle of ascending thirds in a B harmonic minor scale. And we keep going around, and it's color-coded, and we do the same thing. We associate each point with the wedge that it's in, and for the first 16, we get this line. And we can fill it up with even more. This gives us the next, filling up the first 128. When we do this, we have a sequence like this. And the job then as a composer is to try to take this sequence and make something memorable, and also to try to hide the algorithmic structure behind it. And so what I've done here is to move octaves around, to omit certain notes. You can't just skip them because their placement in time is important, but you can substitute rest in for them or have a previous note sustain over. So here is the melody that derives from this process. Okay, and it doesn't sound like it has this self-similar property, but it does, which means we can do all kinds of canons with it, and it will be consistent. So here are a few excerpts. The first one is a 1-to-2 ratio, and we'll play each of these in the full context, but a 1-to-2 ratio, and you can see I've marked tens, and those are the consistent harmonic intervals that you hear. You can have the middle one is a 2-to-3 tempo ratio, again with parallel tenths, and then a 5-to-7 ratio, much more complicated, but still, if you look at each note with its closest pair in the other voices, you are typically getting parallel sixth. Here I'll play a mini version of this. This is the with this line, a canon 1 to 2 to 4. Rubato program for that we heard last night for the end of this. But otherwise, what you're hearing is essentially a series of embellished parallel triads. And that's why it is harmonically gluing together like this. So, Elaine, if you want to join us, we'll start by doing a 2 against 3 canon. And again, Elaine has graciously offered to help. There is excitement in the air because we might fail on any one of these, but we will do our best. The problem was totally mine. So for the next, we have 5 against 7. If we looked at this a long time and worked on it, we could do it, but we're going to teach just a little bit and have click track. Okay, let's take a look at a different kind of canon. So now we are, instead of the thirds or the chromatic scale, now we have just a series of ascending fifths, again going in a counterclockwise direction. And instead of dividing the circle up into these minute slices, instead we're going to have a more musical kind of hierarchical embellishment. So the seconds naturally divide into fifths. The fifths divide into thirds. The thirds divide into seconds. And going back to the top, the seconds can divide back into fifths, etc. So if we do this I'm going to start by taking the sixth, the 6th point there. We have the sequence C, D, E, B, C sharp, A flat, E flat. Okay, and if we fill it in, we will get a melody that looks like this. It's going to accelerate. You see, sempre accelerando. It's going to continuously accelerate. One of the things that we can talk about later if there's time is that there's this relative accelerando between the tempo and the cycle. In the previous example, we held the tempo steady, and you may not have heard it, but the cycle was constantly accelerating or decelerating. In this case, I'm going to keep the cycle steady, and so the tempo has to change. So here's what the melody sounds like. When it gets to the bottom, it's going to repeat to the second line, transposed by a minor third, but I think it'll be clear when you hear it. Okay, since notation programs aren't very good at doing these complex tempo things, I'm going to use this, which is a really, well, it gets the idea across. It's not something you want to perform from, but I think we'll be able to follow it. So let's listen. First of all, this is going to be a 4 against 2 against 1 canon using this, this canon line. Again, you're going to hear parallel major triads as the glue. Okay. Here, let's move to something we haven't heard, which are irrational tempo ratios, essentially pi to e to 1. The disadvantage of an irrational ratio is that you can't play it unless you had click tracks. You can't approximate them. But the advantage is that because it's irrational, once it gets started, they never theoretically line up again in a practical manner. They get close enough that you hear it, but there will never be any sort of periodicity that maintains. So here is an irrational version of this. Again, major triads are the glue. Wasn't part of the canon. I hope that despite all of the activity, I hope that you can hear that they're not only these strides, but they're all basically in the same spot in the circle of fifths as we're going around. That's why there's this largely diatonic feel to it. Another thing we didn't talk about, I don't think, were crab canons, where you take the canon line and you run it backwards. You could do this. If you look at the green arrow in the middle, it shows what we've been doing, which is starting in the center part and extending outward in a clockwise direction. A retrograde would take you from the outside and take you in a clockwise direction in. There's a problem with this in that they'd be going in opposite directions in the harmonic cycle, and so you would hear something like... And so we would oscillate back and forth between agreeing on what the harmonic context is and disagreeing as much as possible to try to relate keys. So what you have to do is you have to make this retrograde go in the same direction as the original, which means you have to flip it. And if you flip it, the musical equivalent of this is a retrograde inversion. We're going to run it backwards and we're going to flip it upside down. This is what's known as the table canon, because ideally you could put a sheet of paper on a table and two people on opposite sides could read from it, and they would be looking at each other's retrograde inversion. Here's an example of a table canon using the same melody. Major tenths are the glue here. Because they're going in opposite directions, and we heard the accelerando, now one of the voices is going to be slowing down while the other is speeding up. Okay. I won't talk about this. You will hear it. All this is going to be in the piece that will be performed tonight. You will hear this version. You can embellish these things in various ways. In the interest of time, I'm going to skip over this for now and take a look at a third and final canon line, which is very much related to the one we just heard. Instead of perfect ascending fifths, we have diatonic descending fifths. The line is going to continue to accelerate throughout. I'll play it through a couple of times so you get the feel of it, and then Elaine and I will do a variation. Again, it's maximally self-similar. We can do it in any kind of combination. 7 against 3 works really well for this one. This is what it would look like if I wanted to notate it accurately. I don't, because this is a horrible thing to look at. So we're not going to look at that. Again, we're going to use some click tracks and read off of something like this. The glue in this, well, I can't remember if it's a 6th or a 10th, but basically what you're going to hear is something that you've heard over and over again in listening to classical music, which is a descending circle of fifths with embellishment. But because it's 7 against 3, we're going to have this odd, non-aligned aspect to it. We thought it was better without resolving it, so we left it there. It doesn't resolve tonight either. Okay, that's the end of my talk. Again, thanks to Elaine Cho. There'll be a concert this evening. The Tong Quartet will be performing canonic offerings where I take a few of these possible combinations and put them together. We'll also be hearing a premiere by Dimitri Tomasco, as well as the Goldberg variations that we were talking about. You can go to my website if you want to look at this or similar sorts of things. Thanks.